We are live now. We are live. We are live. We are live. So, hello, my dear friends. Hello. Hello. I hope you are seeing me fine and I'm audible. Today, we are going to do the radioactivity. Our second topic from the chapter nuclei. Radioactivity. This is what we are going to do today. This is the topic. This is about me. This is about me, Raghav Sharma. Raghav Sharma. MSc Physics, BSc Physics, B.Ed, published an international article in this journal of the American Society, done work with some researchers in JNU. So this is about me, and this is first. Before that, do tell me how's the preparation of the exam going on. How's the preparation exam going on? If it is going bad, you can rate it 1. If it is going okay, rate it 2. And if it is going good, then rate it 3. After that, this is today's goal. First, we are going to do the radioactivity, then alpha decay. Then we are going to talk about the energy in alpha decay, or you can say Q value, and momentum conservation, from which we can get these two things: kinetic energies of the atoms and of the alpha particle. And before doing all this, there is also a question time, in which we are gonna do what? In which we are gonna do the questions. So first, radioactivity, alpha decay, energy, Q value, momentum conservation, kinetic energies of the alpha particle and the daughter atom that has created in the process, and there's so much questions. Before that, make sure you are subscribed us in the our platform at the JEE. Make sure you are following us on LJE, where we provide free PDF material, give you the notification about the free classes, and do the various announcements, and also provide you discounted prices announcements, and also do giveaways. We also do giveaways, so make sure you subscribe us on where? On the JEE, capital JEE. Make sure, and after that, make sure that you have subscribed us on where? On the YouTube. And YouTube, make sure that you are subscribed. Make sure that you are subscribed us on YouTube, and where we post our YouTube videos. So this is our course looks like 90 plus classes, convenient educational platform, and you can watch us in phone, on the YouTube, and on browsers, on laptop and PC, wherever you want, whenever you want, you can watch us. Syllabus made from JEE experts. Okay, this syllabus is made from JEE experts. And flipped classroom method. This is the thing that we are introducing. This thing I will talk in the end of our videos. And we have doubt solving practice, DPPs we provide, and make sure that you do that. So this is our course looks like. Our course looks like. And there are some plans. There are 3 types of plans: light plan, smart plan, and professional. In light, smart, professional, we have all these 4 things. You will get interactive live classes, structures, course and PDFs, live tests, physical notes, and in smart and professional, you will get 3 things more: one-to-one mentorship, live doubt solving, and mock tests regularly. So you get these 3 things. Mentorship, I think that is very much necessary when you are preparing for the exam. That thing is necessary. And the mock tests are very important stuff too. When you're preparing for the exams, you need the questions. You need questions which are important. You need the relevant questions. and the live doubt solving. I don't have to tell you about that, how much it is important. And in professional, we have additional special courses. If you want, you can get motivation from watching additional special courses. If you want, this is on you. So this is what we have: light, smart, and professional. After that, let's start our topic: radioactivity. Let's talk about the radioactivity. Radioactivity. Tomorrow, yesterday we have talked about isotopes. We have talked about isotopes. Okay. So there are many elements. There are many elements in what? There are many elements in what? There are many elements in our periodic table, and each elements has various what? Has various isotopes. So overall, we have around 1500 nuclides. 1500 nuclides. They are all are different. So we have around 1500 nuclides. 1500 types of different what? Nucleus. We have 1500 different types of what? Nucleus. From which around 1250 are unstable. Majority of them are what? Majority of them are unstables, and only you can say around 260, less than 260 are stable. Less than 260 are stable. So what happened them? So what is the thing? What is the thing happening with them? They are emitting what? They are breaking down apart and emitting some stuff and getting what? Getting stable. So only what? Only around 250 are stables and less than 260 are stables. After what they do? So we have an unstable atom. What it can do? It can emit an alpha particle or a beta particle or gamma wave, or can do them all. What it can do? It can emit alpha particle, it can emit beta particle, or it can emit gamma wave, or it can do them all. After emitting this stuff, what will happen? There will be a stable atom plus what? Plus there will be a particle. There can be alpha particle, beta particle, and there can be all of them. So that's how radioactive, what it emit, what radioactive particle it emit radioactive particle. It emit what? Radioactive particle. Alpha particle or beta particles are called what? Radioactive particles. They are called radioactive particles because they have kinetic energies. They have very high kinetic energies when they got emitted, and they have what? They have penetration power. So that's why they called what? They called radioactive particles. That's why they called what? They called radioactive particles. Are we clear? Yes. After that, the spontaneous emission of this is the definition of radioactivity. This is called what? Definition of radioactivity. This is the definition of radioactivity. So what is happening? There is an emission of alpha particles or beta particles or gamma waves for unstable nuclei. That emission is called what? That emission is called radioactivity. So this is the definition. Make sure you are sitting with pen and paper and writing the stuff. you have to make the habit of taking notes. You have to make the habit of taking notes. And when we are doing questions, make sure you are doing with me, or doing, you know I'm doing question, make sure you complete question or do question before me. Okay. So if you are doing that, so you are doing good. You are doing good. And I think you can be the one who will crack the JEE. So some habits has to be from the toppers. So make sure you have those habits. So make sure you are sitting with pen and paper are necessary, or make sure you are making notes. After this, the radioactivity, another, the rate of emission and of alpha, beta, gamma depends on the concentration of the nuclei. Yes, it depends upon what rate of emission, how much alpha particles, how much beta particles, how much gamma particles are going to emit. It's depend upon the nuclei. And this is given by what? Law of radioactivity. We will do it. Okay. Law of radioactivity. This is given by what? Law of radioactivity. The rate of emission depends only on the concentration of the nuclei. After that, radioactivity is a nuclear phenomena. It is a nuclear phenomena. So it is understood, it is understood, or you can study it by, you can simple word is studied. Okay, studied by quantum physics. Just the basics we are doing, just the basics. So just giving you the brief introduction. It is studied by the quantum mechanics. So in here Newtonian mechanics fail. You can't apply v is equal to u plus at. You can't apply this. You can't apply this v squares minus u square 2 equal to as. So here these types of things fail. It is studied by what? It is studied by the quantum mechanics. You don't have to do it. Just I'm telling you, it is done by the quantum mechanics. There is a very famous example of Schrodinger's cat. You can't tell that when it is in box, you can't tell without seeing that it is alive or it is dead. That it is alive or it is dead. After that, radioactivity. So the radioactivity, it is unaffected by the parameters like pressure, temperature, and other physical conditions. It doesn't depend on that. It doesn't depend. Like it is like the gravitational constant. Gravitational constant doesn't affected by the what medium. Take two particles, place them in water, place them in ice, place them in a vacuum. The gravitational force between them is going to be what? Equal. Similarly, whatever is the pressure, whatever is the temperature, whatever is the other physical conditions, radioactivity is going to be remain what? Unaffected. It doesn't so it doesn't get affected by the physical parameters. Okay, so this is what the radioactivity. It is unaffected by the change in pressure, temperature, and other physical quantities. There is a very basic thing, temperature. So who discovered it? We are just doing the basics things right now till here. So to create your interest. So there is a very famous study, a very famous story. It is discovered by whom? It is discovered by Henry Becquerel. By whom? Henry Becquerel. So how he discovered this? Actually he was studying X-rays. He was studying X-rays. X-rays, okay. So he was studying X-rays, and X-rays was, there is a very famous name. X-rays discovered by scientist Ron. His name I know. I don't know how to spell it. Ron scientist. Ron scientist. He discovered X-rays, and he was studying X-rays, and he was studying X-rays. X-rays creates a photographic image, like, so he discovered, he was doing these things, experiments on what? Uranium. He discovered those things on uranium, and he sees that there is a penetration in the rock salt in the photographic plate that can't be expressed by this phenomena of the X-rays. After another year, 1897, then there is Pierre Curie and Marie Curie. Marie Curie, his name was. So she given the laws on it. So that's how the radioactivity got discovered. That's how the radioactivity got discovered. Marie Curie discovered the laws. Given the radioactivity law in 1897, and 1896 Henry Becquerel accidentally discovered them by doing experiment of X-rays on the substance, on the uranium salts. That's how he did it. And actually he got Nobel Prize for that work. He got the Nobel Prize for that stuff. So make sure what you are doing it great. You are doing with it heart. So just give your heart the whatever thing you are doing. Now let's get to the main part. Important stuff. Now we are rolling. So you know now what is radioactivity. You know what is radioactivity. You know that. Okay, now you know that. Now which nucleus tables we talked about? We are talked about 1250 nucleides. Okay, we talked about, and I have said around only 250 are stable. So now we are going to differentiate this stuff into two types. First, when the Z is lower than 20, and the second when Z is greater than 20. When the Z is lower than 20 and when the Z is greater than 20. Are we clear? Z lower than 20 and Z greater than 20. How to know? On the first condition, when the Z is lower than 20. When the Z is lower than 20. How to tell that the nucleus is stable or not? At this, the ratio of N by P. If it is around 1, then the nucleus is said to be what? Stable. If that ratio N upon P, if the ratio N upon P is around 1, so we can say that it is what? It is stable. Let's say, for example, let's have some examples. For like C. Let's take this example of carbon, 6C12. We know it is what? We know it is stable. It is stable. It has 6 protons, 6 neutrons. It is 6 protons, 6 neutrons. Its N by P ratio, it will be 1. Another example, of the nitrogen, it has 7 protons, 7 neutrons. Its ratio n by p, it will be 1. Now let's take another example. 16O8, oxygen, 8 proton, 8 neutron. Ratio will be 1. So if the z is lower than 20, if the z is lower than 20, if the z is lower than 20 and its n by p ratio tends to be 1, if its ratio n by p tends to be 1, then we can call it as a stable atom. Then we can call it an stable atom. Okay, this is for the z when the z is lower than 20. Another condition. I am erasing all these things. So make sure you have written it. Am I erasing? I am erasing all the stuff. Now. Second we have when the z is greater than 20. When the z is greater than 20, then this ratio has to be larger than 1, and has to be lesser than 1.6. Has to be lesser than 1.6. Let's take for example, which is the most stable atom, that is iron, Fe 2656. Its n by p ratio, so it's 26 protons and 30 neutrons. Its n by p ratio will be 30 upon 26, greater than 1, and I think it will be around 1.2 or 1.3 something. It will be 1.3. So n by p ratio has to be greater than what? 1, and has to be lower than what? 1.6. Let's take another examples. This, its n by p ratio, it has 47 protons and 56 neutrons. Okay, 56 neutrons. Its n by p ratio will be 56 upon 47. It is going to be greater than 1, but it is going to be lesser than 1.6. Going to be lower than 1.6. After. Are we done till now? I am again erasing it. So make sure you have written it. 3, 2, 1. I am erasing all the stuff. Yes. And the for third condition, z is greater than 87. There is no stable nuclei. When the z is greater than what? When the z is greater than 87. When the z is greater than what? 87. There is no stable nuclei. When the z is what? Greater than 87. Okay. Now we are at the alpha decay. Now, are we clear about that? After that, we have alpha decay. We have what? We have alpha decay. What it does? It happens to increase to increase n upon p. If it emits alpha decay, what will happen? N by p ratio increases and tries to reach stability and tries to reach stability. And it tries to reach what? It's try to reach stability. The purpose of the alpha decay is what? To increase n by p and to reach the stability. Are we clear? Are we clear? Are we clear? Are we clear? So this is what alpha decay does. This is what the alpha decay does. There can be three types of decays: alpha, beta, gamma. So what alpha decay does? It increases the n by p ratio, and because of that it tries to reach what? Stability. It tries to reach stability. So first thing first, alpha decay. So what is the alpha particle? What is the alpha particle? What is the alpha particle? What is alpha particle? This is nothing but you can say it is helium nucleus without electrons. Helium nucleus without electrons. Or you can say double charged He helium ion. This is what the alpha particle is. Helium nucleus without electrons, you can say, or in our language it is double charged helium ion. It is what? Double charged helium ion. What is symbol? Symbol. It is alpha 2 4, or you can say, or helium 2 4. This is what? This is the symbol of the alpha particle. This is the symbol of what? Alpha particle. This is the symbol of alpha particle. After this, charge. What is the charge in the alpha particle? What is the charge? Charge is plus 2e. It is not electrically neutral. It has charge, and it has positive charge. It has what? It has positive charge. Mass. If we are talking about the mass, it has 4 atomic mass unit. It has 4 atomic mass unit of mass. After that, if we talk about how it happens in what? In our reactions. In reaction, how it does in reaction. So alpha emission, if we talk about the alpha emission, what happens? Like there is a X atom, okay, ZA. Mass number is A, atomic number is Z. And mass number is A. If it is goes in what? Alpha decay. If it is goes in alpha decay, what will happen? A daughter, this is parent atom. This is parent atom. And this is daughter atom. So its atomic number and mass number will decrease by sorry 2, and this at A-4, and plus there will be in what? Helium, or you can say alpha particle, and there will be what? The alpha particle. So this is how the alpha emission looks like. This is how the alpha emission looks like. X, parent atom. This is what? Daughter. This is daughter atom. This is daughter. And this is our alpha particle. This is our what? Alpha particle. This is our alpha particle. So there is a conservation There is a conservation. And what is the conservation in nuclear reaction? There is the conservation of mass number and the conservation of, tell me conservation of what? Atomic number. Both sides, they are going to be what? Equal. They are going to be what? They are going to be equal. A minus 4 plus 4, A minus 4 plus 4, A, Z minus 2 plus 2, Z. So on both sides, the value of A and the value of Z are what? Are equal. Are equal. Are equal. Are equal. Let's take for examples. Let's take example. Let's take example. Let's take the example of uranium. Uranium 238 92. After going alpha decay, it will become thorium 92 90 and 238 234 plus He 9 2 4. So overall 238 234 plus 4 238 92 90 plus 2 92. In alpha decay, there is a conservation of mass number and there is conservation of what? Atomic number. In alpha decay, there is a conservation of mass number and the conservation of atomic number in alpha decay. Question time. Now we are at the question time. Question time. Alpha particle consists of two protons only, or two protons and two neutrons only, two electrons, two protons and two neutrons, two electrons and four protons only. What is the right option? It is two protons, it is two protons and two neutrons, or it is two electrons and four protons only. What will be the answer? What will be the answer? Answer will be two protons and two neutrons only. In alpha particle, there is no electron. There is only what? Helium, which has two proton and two neutron. And what is the charge? Charge is 2 plus. 2 plus, it says that it has 2 plus 2 positive charge. Okay. So it has no electrons. It has no electrons. Yes. Let's see if you can do that. Another question. Next question. Do give a rate. A deuteron is bombarded on oxygen nucleus, then an alpha particle is emitted. The product nucleus says a deuteron, we have emitted an what? Deuteron 1h2. Deuteron has one proton, one neutron, 1h2 we have bombarded in, and then what will happen? I am writing the question. There is an oxygen 816 and plus there will be a neutron. Neutron is 1h2. So 2 will be, and this, and an alpha particle is emitted. Then what? What is going to be here? What? 16 plus 2 18. 16 plus 2 18 minus 4. 16 plus 2 18 4. There will be what? Nitrogen. N. 8 plus 1 9. 9 minus 2 7. So there will be this. 7 and 14. This will be the correct answer. This will be the correct answer. Now let's try to do this. Which race contains positive charged particles? Verbo, very good. Which race contains positive charged particles? Positive. We are talking about positive. Which rays are positive? Alpha, beta, gamma, X-rays. We have just done it. Alpha. Beta are negative. X-rays are what? Neutral, and gamma we will talk about it. So alpha rays are the correct answer, and you know it. They are what? Helium nucleus positively charged with the charge 2+. Yes. After that, try to do this. This is the I think you have done it, chemistry. Equation can be written like this. What it does mean, the equation is like this. Should I do it? Should I? Are we clear? Try to do this question. I am waiting for your answer. X and A 3 7 Li, then X, what will be the X? Like this equation, like this plus, we don't know this, what is this? So this is like n, there is n, so n 0 1. I'm writing the equation. There is Li 3 7 plus, and there is alpha He 2 4. Now can you do it? Yes, option A. Now can you do it? Can you do it? Let's say here, atomic number dash, let's say x plus 1 is equal to 7 plus 4. So x will be what? 10. Where is 10? In option A. If equation written like this, x and alpha, and there's lithium 3 7, this means the reaction is x plus n equal to alpha plus lithium. Okay. This is also a way to write an equation. What equation? Option answer is A. Okay. Up next, we have another question. Alpha particles are they are neutrally charged. Are they positron? Are they protons? Or are they ionized helium atoms? And are they ionized helium atoms? What are they? They are ionized helium atoms. Okay. Next question. We are at the next question. The mass of alpha particle is option A, less than the sum of masses of 2 protons and 2 neutrons, equal to mass of 4 protons, or equal to the masses of 4 neutrons, or equal to the sum of masses of 2 protons and 2 neutrons. Less than the sum of masses of 2 protons and 2 neutrons, equal to the mass of 4 neutrons. What is the alpha particles? Let's first write alpha particle. And it is He24. it has two neutrons, and it has two protons. It has two neutrons and two protons. So it is equal to the mass of 4 protons, equal to the mass of 4 neutrons, or equal to the masses of 2 protons and 2 neutrons. What will be the answer? Yes, answer A. Less than the sum of masses of 2 protons and 2 neutrons. When we combine the 2 neutrons and 2 protons in an atom, there will be a loss of some energy, binding energy. Some energy gets lost to bind them together. So the overall mass will be less than, it will be slightly less, only a little bit. So less than the sum of masses of 2 protons and 2 neutrons. B wrong, C wrongs, and D also wrong. Answer will be A. Answer will be not D, not D, not D, not D, not D, not D. Answer will be A. After we will study binding energy. We will study binding energy. In binding energy, what happened? The overall mass of the atom, overall mass of the atom will be slightly less than the what? Overall mass that has to be happen. So there is a mass defect. So there will be the mass defect. Delta M. There will be what? There will be the mass defect. There will be mass defect, and delta M C square. Delta M C square. This energy is called what? Binding energy. This energy is called what? Binding energy. This energy get lost. Okay, this energy get lost to bind what? Bind the atom. Sorry, bind the nucleus. To bind the nucleus. So this energy get lost. This energy get lost. Lost. So this energy bind the nucleus as it is. There is a very much high interaction. When we are trying to bind two proton, how much energy is needed? So that energy, where this energy come from? This energy come from this binding energy. That's bind two protons and neutrons. That binds two protons and neutrons. So the energy, some mass will get converted into what? Some mass will convert into what? Some mass will convert into energy. And that energy will counter what? Coulombic force. The energy, let's try to do what? In your home, bring two magnets and try to join together. Try to join them together. You will see there will be a very high repulsion. To bind them together, if you want to hold them together, you have to apply very much energy. That energy come from where? At the atomic level, that come energy from binding energy, from the mass defect. We will study it. So I think everyone has starting trick question. Okay, trick question. Option A. Answer will be option A. I think clear. If you have any doubts, I can explain again what is mass defect and what is binding energy. And I am doing radioactivity first because these things will create an feeling. These things will create a feeling. And after doing this, those topics will become very easy. Those things we will do in later chapters, binding energy and mass defect. But we are going to use them here. Mass defect and binding energy. After this, we have energy in alpha decay. Now we are going to talk about mass defect. The students which have done this question wrong, just see this. This is the parent atom, X, Z A, and it goes like this: Y Z minus 2 A minus 4 plus HE HE 2 4 plus energy plus energy. This thing was in rest. Now, if you see A, and this all things are what? Equal. Conservation of A, conservation of Z is happening in alpha reaction, alpha decay. But we have energy. What we have? We have energy. We have energy. From where this energy coming from? From where this energy is coming from? From where it is coming? From where this energy is coming? If you see delta M, the mass of X atom minus mass of Y atom plus mass of helium atom is not zero. Is not zero. Actually, it is greater than zero. Mass of this atom of X atom is greater than the mass of Y plus mass of helium atom. So where this mass defect is coming? This is called what? This is called mass defect. This is called what? Mass defect. Mass of X atom is greater than mass of Y atom and mass of helium atom. This mass is greater than this two mass. So there is a mass defect coming where this mass is getting lost. This mass is getting converted into what? Into energy. This mass is getting converted into what? Energy. This mass is getting converted into what? Into energy. And my dear friends, this energy is not small. This energy is not small. This energy is in order of mega electron volt. Mega. We are talking about mega. So this energy is not small. This energy is not small. You can compare this energy. You can drop some uranium and atom bomb in Hiroshima. America dropped some bombs in Hiroshima and Nagasaki, and you know how much energy is released. So my dear friends, this energy is not small by any way. At delta m c square. So that's how it can in one nucleus there can be two protons. Proton Coulombic force, there will be very high repulsion, so it can hold. So from here you can understand what is delta m. What is delta m? Okay, so energy is what? So this energy is what? Energy of an alpha decay, or you can say Q value, and this is, if you write, this is mass of X atom minus mass of Y atom and mass of helium into C square. And if you want to write, it can be written as delta m. It can be written as delta m into 931.5 mega electron volt, where delta m is in AMU, in atomic mass unit, where delta m is in what? In atomic mass unit, and the Q we will get in here will be in what? Mega electron volt. In mega electron volt. This is shortcut. Okay, shortcut. This is shortcut. Delta m, sorry, q will be delta m c square, delta m into 931.5, and this will be in mega electron volt, where delta m is in atomic mass unit. Okay. Now we have done it. Now we know why the answer is A. Why the answer is A? Now we know. Now we know why the answer is A. I think I have cleared it. Now let's talk about the momentum conservation. Suppose we have an atom, X atom resting, and it has degenerated into two atoms. No, alpha decay happened. It has converted into what? Y and alpha particle He. Initially momentum should be 0. Initially momentum is 0, and overall momentum of those both also has to be 0. But we are talking about the conservation momentum. Total initial momentum should be equal to the final total momentum. We are talking about the conservation of momentum. So the initial total momentum has to be equal to the final total momentum, Pf0. But P alpha means Py has to be equal to what? Plus P alpha has to be 0. Means Py is equal to minus P of alpha. What it means? Py is equal to minus P of alpha. What it means? It means their magnitude is same. But direction is opposite. But direction is what? Opposite. Direction is opposite. Magnitude is same. This momentum is same, but their direction is what? Their direction is opposite. And we can write Py square is equal to P alpha square. After this we can write my square, Vy square is equal to m alpha square and V alpha square. And from here we can write, we know that kinetic energy is, let's say kinetic energy T is what? P square by 2m. So P square will be 2m T. P square will be 2m T. So 2m alpha and T alpha is equal to 2my and Ty, where T is kinetic energy, 2 cut, so it can be also written as Tm alpha, T alpha is equal to my Ty. This can also be written m alpha T alpha equal to my Ty. Thank you Adhyan with Kaushal, thank you. So it can be written as this form. Now let's do the question. A nucleus of uranium decays at rest into nuclei of thorium and helium, then the helium nucleus, let's try to do this question. The helium nucleus has more momentum than the thorium nucleus. The helium nucleus has less kinetic energy than the thorium nucleus. The helium nucleus has more kinetic energy than thorium nucleus, or the helium nucleus has less momentum than the thorium nucleus. What it will be? What it will be? Momentum, momentum we know is same. Momentum is no we same. So if you're talking about the momentum, it is same. It is no less, no more. It is what? It is same. Only the direction is different. So what we can talk about? We can talk about the kinetic energy. Who has more and who has less? Who has more kinetic energy and who has less kinetic energy? We know this m alpha t alpha is equal to my ty. Here y is what? Here y is what? Thorium. Here y is thorium. Here y is thorium. Thorium. TH. Now. Yes, you can see, as you can see, the T alpha, kinetic energy of the alpha is going to be greater than what? Kinetic energy of thorium. Kinetic energy of what? Alpha particle is going to be more than what? Thorium particle. So answer will be C. How? You know the mass of the thorium is high and mass of the nucleus alpha particle is less. So in order to balance this equation, this term has to be greater and this term has to be lesser. So T of alpha is going to be greater than T of thorium. So the right answer will be what? C. C. Now let's talk about the kinetic energy of what? Kinetic energy of alpha particles in terms of Q. Now let's talk about the kinetic energy. Kinetic energy of the thorium particle, of the alpha particles. What is the exact formula? So who are live right now? Try to see things, try to do these things. Make sure you are doing with me. If you are not doing this in pen and paper, you are not going to understand that how the equation are going to come. So make sure you are sitting with pen and paper. First, kinetic energy, Q. Q is the what? The energy released. And this energy released is released in the form of what? In the form of kinetic energy. It is released in the form of kinetic energy. When it breaks, one particle will go this side, one particle other side, and they will have what? They will have kinetic energy. So the energy they release, it released in the form of kinetic energy. So the daughter atom and the alpha particle have what? They have what? Kinetic energy. They will have kinetic energy, and the kinetic energy will be equal to the kinetic energy of daughter atom and the kinetic energy of what? Alpha particle. Equation 1. Okay. Equation 1. Now we can write this as half my, half mv square. I am writing just half mv square, vy square plus half m alpha v alpha square. Okay, are we clear till now? And we know that m y square vy square is equal to m alpha square and V alpha square. We know it. We know it. We know it. We know it. So what can we do? We have to find the kinetic energy of what? Alpha particle. We have to find the kinetic energy of what? Alpha particle. So what we can do? Half my square multiply by my and divide by my plus half m alpha v alpha square. This thing is equal to this. So we can replace it. We can replace it. So half m alpha square v alpha square m alpha square my plus half m alpha square and v alpha square. We can take half m alpha v alpha square common, and this will be m alpha my plus 1 will be left out. This is q, and this is kinetic energy of what? This is kinetic energy of alpha particle. And if we take this my, this will be m alpha plus my. Okay, so what will the T alpha kinetic energy? Kinetic energy will be q my upon m alpha plus my m alpha plus my. Okay, T alpha is what? T alpha is what? Q value, and my upon m alpha plus my. Make sure you are following me, that how the things are going on. Make sure you are following me how the things are going on. Okay, make sure you are following me. Now we know that m alpha, we can write it as atomic mass in AMU. We can convert this in atomic mass unit. We know, we have done this in yesterday class. So A minus 4 into atomic mass units, its mass number is A minus 4. My reaction. Z minus 2 A minus 4 plus He24. So A minus 4 AMU m alpha, and what is alpha? Alpha is 4 plus A minus 4 AMU, atomic mass unit. Cut. So what we have? T alpha is Q A minus 4 by A. So now we have the main formula. That is kinetic energy of the alpha particle is Q value into A minus 4 by A. A minus 4 by A, and this is important. This is important. Make sure you got that. Make sure you got that. Okay, make sure you have got that. Now let's talk about kinetic energy of daughter nuclei in terms of Q. In similar way, we know that Q is half. Similarly, we are going to do this. M alpha V alpha square plus half my Vy square. Okay. Now we have to remove what? We have to remove alpha. So we will do this. M alpha square V alpha square M alpha plus half My Vy square. Now we are going to replace this. We are going to replace this because we know M alpha square V alpha square is equal to My square Vy square. We know this, so there will be half My square Vy square upon M alpha plus half My Vy square. Okay, okay. Now let's take half My Vy square out. So Q will be half My Vy square out, and we have My plus M alpha plus 1. We have this. This is what kinetic energy of what? Daughter nuclei Ty. So Q is equal to Ty, and this will be M alpha My plus M alpha. So Ty will be what? Ty will be Q into M alpha plus My. Okay. Now again we are going to convert it into what? In mass number. So Ty M alpha 4 AMU, and this is M alpha 4 plus My A minus 4 AMU. Cut. So Ty will be what? Q 4 cut 4 by A. The kinetic energy of the daughter atom will be Q into 4 by A, where A is the atomic number of the parent atom. Okay. Important, you can say it. You can ask that. Okay. Now question time. We have question time. So we have the reaction uranium getting transformed into what? By the alpha reaction, thorium plus alpha particle. So we have to find the Q value, kinetic energy of the alpha particle, and the kinetic energy of what? Thorium atom. We have to find three things: Q value, kinetic energy of the alpha particle, and the kinetic energy of what? Thorium atom. So first write the equation. First we are going to do what? We are going to write the equation. Equation is like this: U 92, I think 92 is the atomic number of this, 238 mass number, and this is like pH. Okay, 90 234 plus 4 He2. Now he is asking for the Q value. So the Q value is what? Q value is first Q value. Q value is delta M by C square. Delta M by C square. So the mass of the uranium 238.058. In AMU he is given us in AMU 058. Okay, so we have to multiply it by 931 minus 234.0436 plus 4.0002, 2 times 0, let's add 40436 plus 4002. This will be 654. Okay, and this is 238.0456. 238.0456 into 931 into 931.5. 931.5. So this will be 0.0124 AMU. Okay, AMU, and this will be has to multiply by the 931.5, and answer will be this. I am doing this 11.6 mega electron volt. So the Q value for this reaction and delta M is 0.0124 AMU. Mass defect in this process is 0.0124 mass defect, and the Q value is 11.6 mega electron volt. So the Q value is 11.6 mega electron volt. Q value is 11.6 mega electron volt. Second question, kinetic energy of what? Kinetic energy of alpha particle. Kinetic energy of alpha particle. E alpha. This is Q. Now this is easy stuff. Now this is easy. A minus 4 by A. Q 238 minus 4 upon 238. Now this is writing. Now this is like a writing when we do write in the last of the question paper. Now when we exams, writing will become like this in last. So this will be 238 minus 4 upon 238. So this will be 11.6 into 234 by 238, and this will be 11.4 mega electron volt. Answer number 2, 11.4 mega electron volt. Answer number 2. Now we have given two things, first and second. Third, kinetic energy of thorium atom. So we know that Q is equal to T alpha plus T y. So Ty will be Q minus T alpha. So 11.6 minus 11.4. So this will be 0.2 mega electron volt. So you can see here the more most of the energy has gone to the has gone to the alpha particle, and the daughter atom has only 0.2 mega electron volt, while the alpha particle has 11.4 mega electron volt. You can just see how much T alpha how much greater than is from the daughter atom. How much more kinetic energy it has from the daughter atom. After this, we have how our class looks like. So first we provide theory and do previous year questions. Nearly all the previous year questions we do. Then we will provide you study material from where you can solve your doubts which you have. And after this, there is a webinar we conclude, we do, in which we clear your doubts. If you have some, we will clear them and do more questions, because questions are the key. After this, we provide you homework and we check them, and we also provide you the solution of the videos. So make sure when you give you DPP, give you questions, so make sure you do them. Make sure you does them, and see you soon in next lectures. Till then, take care of yourselves and make sure you follow the guidelines. And 6 feet distance is necessary. 6 feet distance is necessary. So make sure you does that. Okay, see you. Bye bye.